In the previous video, which you can see its link somewhere above, we've solved RMQ problem in ON for preprocess and O square root per query. In this video, we will improve that to answer queries in O1. Hey everyone, I'm Amirza Purakavan. Welcome to Algorithmic Academy. Let's review the problem again. The problem name describes itself. We've given an array and we'll face multiple queries in form L and R. We need to find the minimum element in that range. In the last video, we used the idea of making blocks of size square roots. Consider the array size to be 1 million. We've made blocks of size 1000, as you can see in the slide. But why we have restricted ourselves to non-overlapping blocks? Here you can see that we have some overlapping blocks. So from each index, we have a block of size 1000 and they are overlapping, and there are something like n blocks at total. With our new overlapping blocks, we can reduce number of operations a bit. So as you can see here, for answering a query, we start by reading the minimum from the first 1000 and again, and we go to the end. If you remember from our last video, we did some single elements from beginning and the end, and we used the blocks in between. Here, we use blocks in the beginning, and we can use single elements at the end. But better than that, we can use a block which covers the end of that query. So they will overlap, but it doesn't matter. So it's not like sum. During calculation of sum of a set, if you count a number twice, it will ruin your calculations, right? But for minimum, if you take minimum of a single element several times, it doesn't matter, so it's okay. But here is a problem. When query size is less than 1000, we can't use any of our calculated blocks because all of them are bigger than our query size. We can iterate over all of these single elements and calculate the minimum, but it's not efficient for sure, right? So we need to do something else. We need to think about the query size when it's less than 1000. So pause the video right now and think of a way to optimize small queries. Give yourself at least 15 minutes. The idea is having blocks of two different sizes. One type of smaller blocks and one group of bigger blocks, like blocks of size 1000 as we had before, and blocks of size 50, the new ones. So these small blocks can help us for answering queries which have size less than 1000, like this. So you remember that when size of query was less than 1000, we were struggling and we used to just iterate over all of them one by one, wasting 1000 operations. But now, with having blocks of size 50, we can use the same method we used with our bigger blocks to solve this case efficiently too. And we just need to have and calculate at most 20 blocks. So these two blocks together can make a very efficient way to solve problem. But what about very large queries? I mean, queries with something near to the size of the array, 1 million. So for very, very big queries, what we are going to do is using something like 1000 blocks, right? And this is again not so efficient because we are handling other cases using something like 20 blocks, but this one, no. So what we are going to do is introducing a new type again, and we are gonna have blocks of size 50,000. They are very big blocks, and there is a problem, you may ask. So for blocks of size 1000, during preprocess, calculating the minimum of them is easy. So the preprocess is relatively fast. But with these new blocks with size 50,000, our preprocess is gonna be so much costly. So during preprocess, we'll make a trick here, and instead of calculating the blocks of size 50,000 using single elements one by one, no, we use the blocks of size 1000 inside it. So we use just 50 operations to calculate the minimum of our big block using the smaller blocks, and also we can use the same trick to calculate the minimum in blocks of size 1000 by using 20 blocks of size 50. So during preprocess, we first calculate minimum for our blocks of size 50, and then for 1000, and then for 50,000. Now for answering a query, we can use our very big blocks of size 50,000 when the query is very big. For smaller queries, we can use 1050 size blocks as we used before. But for very big queries, using these new blocks, very big blocks, we just use 20 blocks again, which is very efficient. So all of these stories, the nested blocks, having 3 types of blocks and so on. So think more to find something even more efficient, that we can answer queries even faster. So now pause the video again and think for at least 15 minutes. Okay, the answer is using blocks of powers of 2 sizes, like having blocks of size 1, 2, 4, 8, and 16, and so on. So to say it formally, for each index, we will keep the minimum of all blocks of size powers of 2 starting from that index. So from I to I plus 1, I plus 2, I plus 4, and so on. So let's see an example. Here is our array, and here you can see blocks starting from the first element, so A0. So you can see there are 4 different blocks. So one is of size 1, which is the array element itself, and again 2 and 4 and 8. So here you can see blocks starting from the second element, and now the third element, and the fourth element, and here the fifth element. And not be surprised that for this new element A5, we don't have a block with size 8. Why? because it goes over the array, so it's not a valid range. So we don't include that. So here you can see all of the blocks for that array in one view. So you can see blocks of size 2, of size 4, and of size 8. Our preprocess is going to be similar to what we did for 50,000 big range blocks in the past section. For range equal to size 2 to the power of k, we use pre-calculated minimums from blocks of size 2 to the power of k minus 1. Like here, for calculating minimum of this block which has length 8, we calculate the minimum first for those two smaller blocks of size 4, which is pre-calculated and already known, and we use minimum of them to calculate the minimum for the whole block. And to answer query. So to answer query, it's very similar to what we did before. You remember that overlapping segments doesn't matter in RMQ, so we can have overlapping segments and easily answer queries. So for our query with length, for example, L, we first find the largest power of 2 less than or equal to L. Let's name it P. And we already know the minimum of the first P elements of our query and the last P elements, right? So the minimum of these two ranges will be equal to the minimum of the range of the query. So we can answer queries is in just O1. That's it. So soon we will dive into the implementation to see all these stories on our code. Okay, here is the problem we are going to solve. The problem is simple. It's just what we covered in our video. So we have an array of n numbers and q queries, and I'm gonna implement the solution and submit to see if my code works. So let's start from getting the input. I read the input like this, and I define a sparse table array like this, and I define the constant LG, which is the logarithm, and I start by going over one by one on powers of 2 like this. And now we have another for loop which goes to n, and here we make sure our loop doesn't go over the array end, as I said. And here the calculation is very simple. The sparse table for I and k will be equal to minimum of a sparse table of I and k minus 1. Note that the base is calculated here, so the sparse table of I and 0 is AI, and also we use the same value from I plus k minus 1. So just to remind you, the right shift works as power of 2 somehow. So 1 and then right shift with size k minus 1 produces 2 to the power of k minus 1. And then we go for reading number of queries, and then we go for reading queries one by one, and then we add 1 to R, because always in coding we go for closed open structure. So the L is closed and inside the range, and R is open, so it's something like L is closed and R is open. So we are gonna answer the query right here. So I will write some code and then make it more efficient. So the first version I write is just for understanding, and then we go for optimizations. While k multiplied by 2 is still smaller than R minus L, multiply k by 2, and then finally that's gonna be easy. See out the minimum of sparse table for like this. It's okay. Sparse table for k is start from I and go 2 to the power of k, and then start from R minus 2 to the power of k and go for to the power of k elements. Print that. It should work, I think. So let's check if it's going to work. Okay, it's printing 2 1s, which is incorrect. Let's print the k to see if it's correct or not for every query. So k is both 1. For the first one it's not true because it's just we should start k from 0. And it says 4 and 1, which is correct. So I go remove this line and now go submitting my solution. I always struggle in this. Hope that this is the correct compiler. And now we submit. And we get accepted. So now let me show you some improvements to make on this code. First of all, we don't need the array A. You can easily just get the sparse table as input. This is the first one. Second one is to make your performance better and make the code more efficient, you should swap these 2 dimensions of code of the array sparse table. So the first one should be LG and the second one should be max n, and you should replace it everywhere in the code. The reason is CPU cache, where we will talk about it later, but right now just know that if you swap these 2 dimensions, your code will be much faster. And the next thing is, if you do this in your code, I mean calculating k each time for each query, your time complexity for answering queries is actually logarithm. So to avoid this, there are 2 ways. Either you can do a for loop here and pre-calculate logarithm for different lengths. So R minus L is length of this query, right? So there are a total of n possible lengths. So you can pre-calculate it here using an array, which is easy. You just write log2i is equal to log2 of I divided by 2 plus 1. And another way to do this is using the function built-in count leading zeros of R minus L, which if you decrease 32 minus that, it will give you the power of the greatest power of 2 that is less than R minus L. And that's it. It was all of the tricks behind the sparse table, and we covered everything about that.